Alright guys, I thought I would start this video by showing you a beautiful picture, and I will be giving one extra point for the final, whomever can tell me in which country this picture was taken. It's one of my favorite trips of all times. Alright, so in this video we're going to be talking about the Henderson-Hasselbalch equation, which is what we're going to use in order to determine the pH of a buffer, whether that buffer is by itself or after the addition of acid or base to that buffer. So first, let's look at the derivation of the equation. Basically, we're going to be starting with looking at the weak acid. Remember that the buffer is made out of a weak acid and its conjugate base, or a weak base and its conjugate acid. Here we're looking at a weak acid equilibrium into hydrogen ions and the respective anion. We then write the Ka expression for that process by taking the concentration of our products divided by the concentration of the reactant. We're then going to be solving for the hydrogen ion concentration. And so the hydrogen ion concentration will be equal to Ka times the acid concentration divided by the anion concentration, and that's how we get this equation right here. We then take the negative log of both sides. So the negative log of the hydrogen ion is going to be equal to the negative log of the Ka plus the negative log of the ratio of these two. Because remember that when you take the log of a product, you can basically add the log of the one part to the log of the other thing that is being multiplied by. Since in this case it's a negative log, is plus a negative, so it becomes a negative. From here, we already know that the negative log of the hydrogen ion concentration is equal to the pH. Similarly, the negative log of the Ka is equal to the pKa. And the last part we leave it as is. So this right here is one of the forms of the Henderson-Hasselbalch equation. This one is actually the form that I utilize just because. And then you can rearrange that equation by actually inversing this ratio, in which case the sign here changes. And so we have another version of the equation, which you will see in the book, that is basically mathematically they are identical, but what changes, and I'll highlight that, is that the sign becomes positive, and the ratio now is going to be the ratio of the concentration of the base divided by the concentration of the acid. Again, remember that a buffer is made out of a weak acid and its conjugate base, or a weak base and its conjugate acid. And so you can use either equation form as long as you put the concentration of the acid wherever it says Ha, and the concentration of the conjugate base wherever it says A minus, right? Make sure that you utilize one, don't mix them up, utilize one form and stick with it throughout your calculations. All right, so here on this slide, I have rewritten the same equations, again in two different forms. As I mentioned, I tend to use this form of the equation, but this other form is identically, mathematically, it will give you the same exact answer. Just make sure that you utilize one and stick with it. If you utilize this one where the acid is on top and the base is on the bottom, then we're going to be utilizing a negative sign here. Now, this equation assumes that the equilibrium concentrations of the acid and the base conjugates that make up that buffer are almost equal to the initial concentrations that they're starting with. And if this is not a safe assumption, then the alternative would be to actually do an ice chart in a similar way to what we did with the common ion effect. However, for most buffer systems, the assumption is valid, and so we will be utilizing these equations for the calculation of a pH of a buffer. All right, the first example is that we're going to calculate the pH of a buffer that is composed of 0.12 molar benzoic acid and 0.2 molar sodium benzoate. Notice that we have benzoic acid, which is a weak acid, and we know that because it is not on the list of the strong acids. And then we have sodium benzoate. Benzoate is the conjugate base of benzoic acid, and it's a sodium salt of that benzoate ion. So we know that we have a buffer even if it had not said buffer. And I want you guys to become familiar with it. I don't have to tell you that this is a buffer. All I have to tell you is that you have a weak acid and its conjugate in the form of a salt, or a weak base and its conjugate acid in the form of a salt. You should then recognize that that is a buffer problem. All right, the Ka for benzoic acid is provided, that's important, and use either an ice chart method or Henderson-Hasselbalch equation, or both, to be able to calculate the pH of that buffer. Now, because of the simplicity of the Henderson-Hasselbalch equation, I highly encourage you to utilize that method, unless for some reason you forget the equation or you don't have access to the equation. So here I will be utilizing the equation. Again, the form that I utilize of the equation is that the pH is equal to the pKa minus the log of the acid concentration, so HA, divided by the A minus. All right, what information do we actually have? We have the concentration of the acid, we have the concentration of the base right here, and we have the value of the Ka. So we're kind of set to go. I'm going to go ahead and write it. So the pH is going to be equal to pKa is the same thing as the negative log of the Ka, and my Ka is 6.3 times 10 to the negative 5, minus the log of the acid concentration, which is 0.12 molar, divided by the base concentration, which is 0.20 molar. And that gives us a pH, which is equal to, for the first part, is 4.20. The second part is minus negative 0.22. And so because of that, our answer is that the pH is equal to 4.42. That's that. Before I move on to the next problem, I want to point out something about the Henderson-Hasselbalch equation that I forgot to mention. So let me come back up here so that we have the notes complete. Now, because we have here the ratio of two molarities of two substances that are in the same solution, so under the same volume, we are actually able to either utilize molarities, or we could utilize moles of the acid and the base. As long as we are utilizing the same unit or the same variable for both of these, we would be okay. Either molarities or moles, both of them would work. If you had used molarities, in reality, remember that molarity is mole per volume, or moles per liter, I should say. And so the liters would have canceled out because they have the same number of liters. And so again, it makes no difference whether you utilize moles or molarity, as long as they're both on the same units. So that's something that is important for you guys to remember. All right, so let's go to the next problem right here. Calculate the concentration of sodium benzoate that must be present in a 0.2 molar solution of benzoic acid to produce a pH of 4.0. The Ka for benzoic acid is provided. So let me highlight the information that we have. We know the concentration of the benzoic acid. We know the pH that we want. We know the Ka for benzoic acid, which is provided right here. And what we're looking for is the concentration of the sodium benzoate. Sodium benzoate is the conjugate base of that benzoic acid in the form of a salt. So we're going to start again with Henderson-Hasselbalch equation. So our pH is equal to the pKa, minus the log of the concentration of the acid, HA, divided by the concentration of the base. In this particular case, I am actually interested in looking for the concentration of the base. So it might actually be on my best interest to utilize the other version of the equation, which is going to be pH is going to be equal to the pKa plus the log of my base divided by my acid. And the reason why I'm choosing this is because now my base is in the numerator. And so that's a little bit beneficial. It might save me a couple of steps of algebra. So from there, the next thing that I'm going to be doing is that I'm going to move the pKa to the other side. Since it is adding to the log, it will come and subtract on this side. So what I have is that pH is equal to, pH, oops. Okay, that works better. pH is going to be subtracted by the pKa, and that's equal to the log of the A minus divided by the HA, which is my acid. Then I want to get rid of the log. To get rid of the log, what I'm going to do is to use the inverse log. So I'm going to do 10 to the pH minus pKa is going to be equal to now the ratio of A minus divided by the HA. Again, what I'm solving for is that A minus. So the last step that I need to do is to multiply both sides by the concentration of the HA to get my A minus. So A minus is going to be equal to the concentration of HA. And sorry that I dropped the brackets initially, but that's my HA times the 10 to the pH minus pKa. And now we can plug in our values, which are going to be the concentration of the acid, which is 0.20 molar, times 10, that's a times, 10 to the pH that we want, which is 4.00, minus the pKa. The pKa we had already calculated it on the previous problem. Let me go back really quickly for you to see where I'm getting that from. Notice that here we had pKa, which was the negative log of 6.3 times 10 to a negative 5 for the benzoic acid, and that gave us 4.20. So I'm going to go ahead and just take the 4.20 here instead of typing the whole thing. And here we have 4.20, and that gives us the A minus concentration as 0.13 molar. All right, this slide I think is actually pretty important again because we're going to be talking about how to select the components of a buffer in order to give you the pH that you require. And this is a really good skill for you to have whether you're going into chemistry, biochemistry, biology, or maybe even healthcare, pre-medicine, pre-nursing, because you will be utilizing buffers for various reasons. All right, so what chemicals would you use to mix or would you use or mix to create a buffer of pH 2.3, and in what ratio would you mix them? So to be able to answer this, let's go ahead and look again at Henderson-Hasselbalch equation, which says that the pH of a buffer is going to be equal to the pKa minus the log of the ratio of the acid concentration, HA, divided by the concentration of the weak base or the conjugate base, if you would. And so, as you can see, what controls the pH of a buffer mainly is going to be the pKa of that buffer. So we want a buffer system or acidic and basic components that are going to have a pKa that is close to the pH that we're interested in. And specifically, as we will talk about in a few slides, we will talk about the fact that that buffer will only be effective within one plus or minus 1 pH unit from the pKa. So if we want a pH of 2.3, then that means that we want the pKa to be within 1 unit of that. So we want a pKa in the range, a pKa in the range of 1.3 to 3.3. Again, plus or minus 1 unit from the pH that we are interested in. And from there, we can figure out what Kas would be associated with that. To be able to get the Ka, we're going to do 10 to the minus pKa. So 10 to the minus pKa. And so for a pKa of 1.3, my Ka ends up being 0.05. And for a pKa of 3.3, my Ka ends up being, let me go ahead and write this down, my Ka here ends up being 0.0005. So basically I need a weak acid, that has a Ka in this range, so 5 times 10 to the minus 2 to 5 times 10 to the minus 4. And ideally, that is as close as the hydrogen ion concentration, or the Ka, of 2.3. So anyways, what you need to do now is to go to a table that lists various weak acids with their respective Ka and find a weak acid that is in this range. And so I went to a table and I found that HClO2, this weak acid, has a Ka that is equal to 1.0 times 10 to the minus 2, which is in the range, is smaller than this one and is larger than this one, and therefore that would work. All right, so from there, what other substance do I need? If I'm going to use HClO2 as my weak acid, I need the conjugate of that weak acid, which would be ClO2 minus, but I need it in the form of a salt. As we mentioned earlier, we could get a salt that utilizes a group 1 metal, such as sodium or potassium. So let's go ahead and say that I'm going to use sodium ClO2. Here we go. And so now I have identified the two substances that I'm going to utilize, HClO2 and NaClO2. Now, I need to figure out what molar ratio to mix them at in order to get the pH that I want for that buffer. And so that's where I come back again to Henderson-Hasselbalch equation. I'm going to take it here. I'm going to say, okay, now my pH is going to be equal to my pKa. Now the pKa is going to be the negative log of the actual Ka of the substance that I have selected, which is 1.0 times 10 to the negative 2, minus the log of that ratio of the two substances. So here's going to be the concentration of the HClO2, which is my acid, divided by the concentration of the conjugate, which is the sodium chloride, or I'm going to put it as ClO2 minus, basically the conjugate of it. And so my job is going to be to solve for this ratio right now. So let me go ahead and rewrite this. pH is going to be equal to the negative log of 1 times 10 to the minus 2 is equal to 2.0. And actually, if you don't mind, I'm actually going to go ahead and replace the pH with the pH that I want. So the pH that I want is actually 2.3. So 2.3 is equal to 2.0 minus the log of the ratio that I want. And I'm just going to rewrite that. So HClO2 divided by ClO2 minus, and that's that. So now I'm going to solve for this. In order to do that, I'm basically going to move the 2.0 to the other side. So I have 2.3 minus 2.0. That gives me 0.3 is going to be equal to the negative log of the ratio again. And I'm not going to rewrite it right now. This is the same thing that goes here. So now we need to get rid of the log. And to do that, the first thing that I'm going to do is actually get rid of the negative sign. So I'm going to multiply both sides by -1. And that means that this negative goes away. And instead, the other side is going to be negative. So I have negative 0.3 is equal to the log of the HClO2 divided by the ClO2 minus. And the last thing that I need to do is to get rid of the log, and to do that I just do the inverse log. So 10 to the minus 0.3 is going to be equal to the ratio of HClO2 to the conjugate ClO2 minus, and 10 to the minus 0.3 is going to be equal to 0.5. And so what that means is that I need a ratio of these two of 0.5, or you could have solved it as the ratio of ClO2 minus divided by the acid, which is HClO2, which is the inverse of 1 over 0.1 of 1 divided by 0.5, which is equal to 2. So basically I need twice the concentration of my conjugate base that I need of the acid, and that would give me a buffer of a pH of 2.3. So just to recap, what you do is that you start by looking at the pH that you're interested in. You will then select a weak acid that has a pKa that is close to that pH that you want, specifically within 1 unit, either -1 or +1 of that pH. You then convert that pKa into a Ka, and you go to a table and you find a weak acid that contains a Ka in that range. Once you select that acid, you then select the conjugate base of that acid in the form of a salt, and then you use Henderson-Hasselbalch equation to solve for the ratio of the concentrations that you are interested in by plugging in the pH that is desired and the pKa for the particular buffer system. Okay. All right, so just to recap, what determines the buffer pH? The buffer pH is determined by the pKa of the weak acid base conjugate utilized and the molar ratio of the weak acid and base conjugates according to the equation given here, which is the Henderson-Hasselbalch equation. Now, the buffers are effective, as we mentioned, in a range that is close to the pKa, and that effectiveness is based on the buffer capacity and the effective pH range. And we're going to talk about those two concepts in the next two slides. So the buffer capacity is the amount of acid or base that a buffer can neutralize before the pH begins to change. So basically we're talking about how much acid or how much base that is added to that buffer can be taken in and can be neutralized before the buffer is no longer effective, basically because the buffer components have been utilized, have been used up. And so for that reason, the buffer that has a higher conjugate acid base pair concentration will have a higher buffering capacity. Basically, if you think about it, if you have more of those buffer components, then it's going to take more acid or more base to consume them, to use them up, right? So this is why having a higher concentration of those buffer components will give you a higher buffer capacity. Now, the second thing that we mentioned that is important for the effectiveness of the buffer is the buffer range. Buffer range is the pH range within which the buffer is effective. The buffers have better buffering capacity if the concentrations of the weak acid and the conjugate base are nearly equal as provided by the Henderson-Hasselbalch equation. When I say nearly equal, it means that they don't actually have to be equal, because if they're equal, then this ratio is 1, and then the log of 1 is going to be equal to 0, in which case the buffer will only give you the pH which is equal to the pKa. But as we saw on the example that we did just a second ago, you could have a buffer that has a pH that is different from the pKa as long as you have the right ratio. So we want this ratio to be close to 1, but it doesn't have to be 1. They just need to be close. Now, what you should remember is that the buffers usually have a usable range within plus or minus 1 pH unit from the pKa. So for example, if my pKa was 2.0, like in the example that we had a second ago, then the pH of the buffer within which that buffer would be effective would be between 1 and 3. Again, plus and minus 1 pH unit from the pKa. And just to remind you, the pKa is defined as the negative log of the Ka. All right, now we're going to be talking about how to calculate the pH of a buffer after we have added a strong acid or a strong base to it. As we saw in the previous video, whenever you add a strong acid or a strong base to that buffer, the pH will change just a little bit, but it does change. And when we add a base, the pH will rise. When we add an acid, the pH will decrease, even if it's just a small change, which is what we're going to calculate now. So the way to do this is that to think about the fact that whatever acid or base you are adding to the buffer will be completely reacted or completely used up or completely neutralized by the buffer components. And after that reaction takes place, the new ratio of the buffer components that are left over is going to control the pH. So what we're going to do is that we're going to be writing an equation for the neutralization of the added acid or added base with the buffer component that it would react with. And once we have that equation, we're going to set up what is known as an ICR chart, which is initial, change, and result, in order to calculate the number of moles of the buffer components that are left. Now, R again stands for results, and the main difference between an ICR chart and an ICE chart is that we're going to be utilizing moles, not molarities. So this ICR chart is really just an accounting table for us to see, okay, this is the number of moles that we are starting with. Once we add the acid or we add the base, what is the end product? How much is left in terms of moles out of the buffer components? Once we figure out the number of moles of the buffer components that are left, then we're going to plug them back into the Henderson-Hasselbalch equation to calculate the new pH. Now let's come back to here. As I mentioned, basically the acid or the base that are added are going to be completely neutralized. If we add acid, that acid is going to react with the basic portion of our buffer. Remember that the buffer has two components. It has either a weak acid and its conjugate base, right? This is the acidic portion of the buffer. This is the basic portion of the buffer. So if I add acid, let's say HCl, out of which H plus is the important part, that H plus is going to react with the basic portion of my buffer, which is the A minus. When they react, the only product that can come out of that is the HA, the acid basically, right? They come together to form HA. So this is the equation that we would utilize whenever we are adding acid. On the other hand, if we add base, that base is represented by the hydroxide ion here. Let's say that it came from sodium hydroxide or something like that. Anyways, that hydroxide ion is going to react with the acidic portion of my buffer, which is the HA. And when they react, that base accepts a proton, forming water, and the acid must act as the proton donor, forming A minus. Right? So again, this would be the equation that will be utilized to set up your ICR chart for addition of base. And then once we use the ICR chart, we would have number of moles to plug into the Henderson-Hasselbalch equation. Let's go ahead and do a problem. So consider a buffer that is made by taking 0.140 moles of cyanic acid together with 0.11 moles of potassium cyanate. So notice that we already have cyanic acid, which is a weak acid, and now we have potassium cyanate, which is the conjugate in the form of a salt. And we have sufficient water to make them into 1 liter of solution. Fine. So that means that I have number of moles, and if I divide them by the liters, I also have their molarities. The question is calculate the pH of the buffer before addition of any acid or base, after addition of some nitric acid, which is a strong acid, or after addition of some base, potassium hydroxide, which is a strong base. And we are also provided with the Ka for the cyanic acid right here. All right, so for number one, basically we're saying that we have just a buffer by itself. And so what we're going to use for that is the Henderson-Hasselbalch equation, which says that the pH is equal to the pKa minus the log of the ratio of our acid, and I'm just going to put HA here, divided by the A minus. And if you don't mind, I'm going to come and relabel. My cyanic acid will be my HA, my acid, weak acid. And the potassium cyanate is going to be my A minus because of the cyanate, basically. It is the A minus. All right. I also will need the pKa, and I'm going to need it for all three parts of the problem, so I'm just going to calculate it here. From the Ka, I can calculate the pKa as the negative log of that Ka, which is 3.5 times 10 to the negative 4. And so my pKa is going to be equal to 3.46. All right, so coming back to here, now I can calculate the pH as 3.46, which is my pKa, minus the log of the ratio of the concentrations. The acid is 0.140, and remember that I can use just the moles or the molarities. In this case, both numbers are the same since the liters is 1 liter, but you're welcome to just use the moles. You don't have to convert to molarities at all because both substances are together in the same volume, and so the volume ultimately will cancel away. For my cyanide ion, I have 0.11. So here we go, 0.110. And that gives me a pH which is equal to 3.36. So we are done with part one, and you can see how easy it is to calculate the pH of a buffer before addition of acid or base. Now we go to number two. In this case, we're adding nitric acid, which is a strong acid, and that nitric acid, we're going to basically be labeling it as H+, right? Because the nitrate is a spectator ion. And so for number two, what we said is that if we were adding acid, that acid is going to react with the basic portion of our buffer. So I want you to first think, okay, what are the components of my buffer? My buffer is made out of a weak acid and its conjugate base A minus. The weak acid is the acidic portion of my buffer. The conjugate base is the basic portion of my buffer. And I'm going to go ahead and write that underneath. So acidic portion, and this is my basic portion. All right, now we said that we are adding acid, which is represented by H+. That H+ is going to be reacting with the basic portion of the buffer because acid reacts with base, and the basic portion of my buffer is the A minus, right? This guy right here. And the product of that reaction is going to be the formation of HA. This is the equation that I'm going to utilize to set up my ICR chart. The I stands for initial, so here we're going to put the number of moles of initial. Remember that I said for ICR chart, one of the important things is that we're going to use moles, not molarities. And I'm going to go ahead and write that here. Oops, that is not an M. All right, so for the H+, this is basically the number of moles of the nitric acid that we are adding, which is 0.015. Then here we're going to put the number of moles of the buffer components that we are starting with, and it was 0.110 for the basic component, and it was 0.140 for that weak acid. We then think about the fact that all of that acid that was added is going to be consumed by the buffer. So the change is no longer an X. We actually know what that change is because it is basically all of that acid, negative 0.015. And that change carries. So for the other reactant, it will also be 0.015. And then for the product, it would be the same number, but the opposite sign, right? So positive 0.015. I can then do the result, and that's just basically by adding whatever I have here. And of course, in this case, that's going to be 0 for that acid because that's the whole role of the buffer. And for this guy right here, the new number is going to be 0.095. And for my weak acid, the end result is going to be 0.155. Now that we have the new values of the buffer components, we're going to use those new values in the Henderson-Hasselbalch equation to calculate the pH of the new solution. So now the pH, again, is equal to the negative log, divided as pKa because we already calculated the pKa, minus the log of my HA, either moles or concentration, and in this case I'm going to use the moles directly, divided by my A minus. So therefore pH is equal to the pKa, which we said was 3.46, minus the log of the new ratio, where the HA is 0.155, 155, and the A minus is 0.095. And because of that, the pH ends up being 3.24. And as always, do a reality check. We said that we were starting with a buffer that had a pH of 3.36, and we added a strong acid to it, so we did expect the pH to decrease because the solution was becoming a little bit more acidic. But we didn't expect a very significant change because it is a buffer after all, and that's in fact what we're seeing. We only have a little bit of a change. All right, so the next part, number 3, is upon addition of a base. So again, we have the two buffer components, the HA and the A minus. This is the acidic component, this is the basic component. In this particular case, we said that we are adding a base. We're adding, let me go back to it, we're adding potassium hydroxide, from which basically the important part is the hydroxide. So I'm going to go ahead and call it OH minus. The potassium is a spectator that is not going to participate in the pH. It's not going to have an effect on the pH. So what I'm going to say is that my hydroxide ion from that base is going to react with the acidic portion of my buffer, which is the weak acid. And then I have to think about what are the products of that reaction. Well, the base acts like a base, meaning that it's going to be accepting a proton and forming water. And this guy will have to be the proton donor, becoming A minus. All right, I will utilize this equation to set up my ICR chart. Here I put the number of moles of the potassium hydroxide that we are adding, and that is 0.015. For my initial weak acid moles, we had 0.140. I'm using the numbers from the very beginning of the problem, right? For the water, we actually don't care. And for the A minus, I was starting with 0.110. From here, we said that the whole role of the buffer is to be able to consume all of the base that was added. So my change is going to be the consumption of all of those moles. So negative 0.015. Therefore, this goes to 0 for my result. And the change is going to carry through. So for any other reactant, I'm going to have a negative 0.015. Which brings this down to a 0.125. And on my products, I'm going to have the same number for the change, but positive, right? The opposite sign, 0.015. And that therefore becomes also 0.125. So now I have the new numbers for my buffer components. And in this particular case, they ended up being the same number, just as a coincidence. It doesn't have to be that way. It depends on the particular problem. So then what I do is that I'm going to use again the Henderson-Hasselbalch equation, which says that my pH is equal to the pKa minus the log of my acid divided by my base, and that's equal to 3.46 for the pKa minus the log of 0.125 divided by 0.125. Oops, 25. So 0.125 divided by 0.125 is obviously the log of 1. And the log of 1 is equal to 0. So basically this whole thing in this particular problem is equal to 0. If we had different numbers here, you simply plug into the calculator and find what the value is. But for this particular problem, we ended up with the pH being equal to 3.46. And again, do a reality check. We started with a buffer that had a pH of 3.36 at the very beginning. And after addition now of a base, we expected that pH to rise by a little bit, and that's in fact what we saw. So we are done. All right, question for you guys. Hydrofluoric acid is in solution with sodium fluoride. If hydrochloric acid now is added, which buffer component will react with that acid to minimize the change in pH? Okay, turn your video off, give it a try. All right, so what we have here is a weak acid, and we have its conjugate base in the form of a salt. So what that means is that we have a buffer system. So even though it doesn't say buffer anywhere here, we have a weak acid and its conjugate in the form of a salt. That should tell you, I have a buffer solution. And so I'm just going to go ahead and write down here. My two buffer components are the HF and the conjugate, because the sodium is just a spectator ion that we use to be able to supply that fluoride. All right, so now I'm adding a strong acid to that. That strong acid, basically the H plus is what's actually going to react. Chloride is another spectator ion. And so the question is, what component out of this buffer will react with that hydrogen ion in order to minimize the change in pH? And so as we said, whenever that acid gets added, it will react with the basic portion of my buffer, which is this guy right here, the fluoride. And in doing so, they're going to be forming HF. So the answer in this particular case is that the fluoride is the component out of that buffer that will be minimizing the effect of the acid by reacting with that acid.